Hello everybody, I am Jithin P from Department of Mechanical Engineering, Rajagiri School of Engineering and Technology, Cochin, affiliated to APJ Abdul Kalam Technological University. Last audio lecture was on mechanical vibration, introduction to mechanical vibration. In that session, we have discussed different types of mechanical vibration systems. We have discussed in detail what actually is meant by a single degree of freedom, undamped free vibration system. We have derived equation motion for undamped free vibration system, both longitudinal vibration systems and also for transverse vibration systems. This session is basically on some solved examples related to undamped free vibration systems. So we'll discuss two examples. One is a pendulum. One example is based on a pendulum, and another one a pulley system. We will be discussing both energy method and Newton's method for solving such problems. So let's move to the presentation. So the first question is, by neglecting the mass of slender uniform rod as shown in the figure 4a, determine the natural frequency of free vibration of mass for small oscillation. The configuration diagram is given. You can see L is the length of the arm of the pendulum, M is the mass of the bob attached to the end of the arm, and K is the stiffness of the spring which is attached to the arm of the pendulum. A is the length, that is the vertical length between the point of oscillation and the spring. This question is asked in Kerala Technology University examination, April 2018. So for solving this problem, we can either use energy method or Newton's method. So for this case, I am using Newton's method for solving the problem. For solving means we need to first find out the equation motion of the problem, and then from that equation motion we need to extract the natural frequency. So this is the free body diagram for the system which is given in the problem. So I am giving a displacement, angular displacement in the counterclockwise direction for the pendulum. You can give the displacement either in counterclockwise direction or in clockwise direction. That's up to you, because initially we need to give a displacement for system to start its free vibration. So in this problem I have given a counterclockwise direction angular displacement. You can see two forces acting on the system when it is displaced towards counterclockwise direction. One is the spring force, another is the weight of the bob. Spring force, we know that it is K into X. K is the stiffness of the spring and X is the deflection of the spring. So we need to find out what is actually the deflection or the stretching happened to the spring. So that can be found from the dimensions given in the pendulum. That is, if you can see, A is the distance between the point O and B. B is the point where the spring is attached. O is the point of oscillation. So A is actually the distance between point O and B. So the spring has been displaced by a distance towards right side. I will show with the pointer. You can see here. Okay, so this is the displacement or the stretching that has happened to the spring. So for finding this stretching or the deflection that has happened to the spring, you can solve this triangle. So this is actually A sine theta, because A is actually the length between the 2 points O and B. B is the point to which the spring is attached. So OB is actually A. So A sine theta is the deflection or the displacement happened to the spring. Similarly, the bob has been displaced by a distance L sine theta. From the point of oscillation, or this line, the bob has been displaced by distance L sine theta, because OC is the length of OC represents length of the pendulum. It is L. OC is equal to L. So L sine theta is actually the displacement of the bob from this line of oscillation. You can see the line, vertical line. From there it is L sine theta. So L sine theta is actually the distance of this weight, distance of this force, or the line of action of the force, weight. Okay, weight of the bob. So the line of action of the weight is at a distance L sine theta from the point of oscillation. The line of action of weight is L sine theta away from the point of oscillation. So, or we can say W, which is the weight of the bob, the perpendicular distance of that force, that is weight, with respect to the point of oscillation is L sin theta. So L sin theta actually is the perpendicular distance between the point of oscillation and the weight. Similarly, A sin theta is the deflection, and you can see A cos theta. A cos theta is actually the perpendicular distance of the spring force with respect to the point of oscillation. A cos theta is the perpendicular distance with respect to spring force and the point of oscillation. Okay, perpendicular distance between spring force and the point of oscillation. So this is the distance. So you understood the figure. So you found out the distance of the forces with respect to the point of oscillation. Spring force is at it is away from the point of oscillation by a distance a cos theta, and weight is at a distance L sin theta from the point of oscillation. And the spring displacement is A sin theta. So this is what we have got from the what are the details which we have got from the free body diagram. Now you can see here deflection of spring is as A sin theta. Theta is equal to angular displacement, and theta dot will be a representation for angular velocity. Theta double dot will be the representation for angular acceleration. And you need to consider this thing, that is inertial torque of the pendulum. In which direction inertial torque is acting? I have displaced the pendulum towards counterclockwise direction. So the inertia of the pendulum will be in the clockwise direction. So here it is written that inertial torque of the pendulum is clockwise direction. Inertial torque, the expression for inertial torque is I alpha. Alpha is angular acceleration. Here instead of alpha, we are using theta double dot. Okay, theta double dot is the expression for representing angular acceleration, because theta double dot is d square theta by dt square, which is differentiating angular displacement with respect to time twice. D square theta by dt square, that is angular acceleration alpha. You can see here. So I alpha or I theta double dot is inertial torque. Inertial torque is acting in the clockwise direction, because I am pushing or I am displacing the pendulum towards counterclockwise direction. So inertial torque is towards clockwise direction. So I hope you have understood the free body diagram. Now we will apply D'Alembert's principle for solving this problem. You can either apply Newton's second law, or you can represent the dynamic equation as according to D'Alembert's principle. Newton's second law, we know that rate of change of momentum. Here it is angular momentum, because the system have a transverse vibration. Okay, system is having a transverse vibration, or the angular displacement is the displacement of the system. So we will consider rate of change of angular momentum of system is equal to net force, or instead of force it is net torque acting on system. So that is our Newton's second law. The rate of change of angular displacement is equal to net torque acting on system. So by D'Alembert's principle, we can write this dynamic equation as a static form. That is, the net moment created by the system of forces acting on system plus the inertial torque of the system is equal to 0. In Newton's second law, we have discussed that we have defined that rate of change of angular momentum is equal to net torque, or the acceleration torque of the system. Here it is writing in the static format, that is rate of change of the net moment due to the system of forces acting on system about a point is plus the inertial torque of the system is equal to 0. So I have discussed in the previous slide that inertial torque for the system which we have considered here is towards a clockwise direction. Why it is in clockwise direction? Because I have displaced the pendulum in anti-clockwise direction, so the inertial torque will be clockwise direction. Okay, I have displaced the pendulum in anti-clockwise direction, so the inertial torque will be clockwise direction. So inertial torque is clockwise direction. You should remember that inertial torque is clockwise direction. Now find the moment due to other forces about the center of oscillation, because we will be taking moment about O, or the point of oscillation. Okay, so first force is spring force. So we need to we can rewrite the equation like this: inertial torque of the pendulum, that is I alpha or I theta double dot, plus moment due to spring force about the center of oscillation or the point of oscillation O, plus moment due to weight of the bob, that is mg, about the point of oscillation O, equal to 0. So there are two forces. We need to find the moment due to these two forces, that is first is spring force, moment due to spring force, and second one is moment due to the weight of the bob. And after finding that, we need to write the whole equation. So first we will find out the spring force. We know that spring force is kx, displacement is a sine theta. A sine theta is the amount displaced by the spring by a pushing or by pulling the pendulum by an angular displacement theta. I have pulled the pendulum by an by an angular displacement theta in the counterclockwise direction, and the spring has displaced by an amount a sine theta. You can see here a sine theta. This is the stretching of the spring. I am pointing it in the on the free body diagram. You can see here. Okay, so a sine theta is the stretching of the spring happened when we have pushed the pendulum towards counterclockwise direction by an angular displacement theta. So a sine theta is the stretching. So that is actually the displacement written here. A sine theta is the value of x. We know that theta is very small quantity. We have displaced the pendulum for a very small quantity. Considering that theta is very small, and we can say that in that case limit theta tends to 0, sine theta is equal to 0. So we can approximate sine theta as theta. Okay, as limit tend to 0, we know that limit tend to 0, sine theta is equal to theta. So we will approximate sine theta as theta. So instead of k into a sine theta, we will write it as k into a theta. Okay. Now we will find the moment of the force, spring force. So moment is force into distance. So force is k into a theta. Distance of that force with respect to the point A. What is the distance of this spring force with respect to point O, not A, point O? The distance is this distance. Okay, this is the perpendicular distance of the spring force with respect to point O, and that distance is a cos theta. Okay, so spring force into distance a cos theta. So k into a theta into a cos theta. That is the moment value by the spring force. Okay, and we have considered theta as very small. So limit theta is 0, cos theta is 1. So we will approximate cos theta value as 1. So we will take this cos theta value as 1. Approximate this constant value as 1. So k into a theta into a into 1. So k a square theta. K a square theta. K into a theta into a into 1. K a square theta. Cos theta is taken as 1. Okay. Now we will find out moment due to the weight. You can see here on the figure that is weight is W. It is acting downwards. And the perpendicular distance of this weight with respect to the point of oscillation. We are taking moment about the point of oscillation. Okay. That is O. About O we are taking the moment. So perpendicular distance of this weight with respect to point of oscillation is L sin theta. L is the length of the arm of the pendulum. That is OC is the length. Okay, so L sin theta is the distance between W and the point of oscillation. So W into L sin theta or mg into L sin theta. Okay, we know that theta is very small, so sin theta can be approximated theta. So mg into L, instead of mg into L sin theta, we can write it as mg into L theta. Mg into L theta. So that is the moment value of weight about the point of oscillation. Now we will write the equation according to D'Ambel's principle, that is I theta double dot, that is inertial torque, plus the moment due to spring force plus the moment due to the weight of the bob is equal to 0. That is what is written here. That is what is written here. Moment due to inertia force plus moment due to spring force plus moment due to the weight is equal to 0. Now you see this, all the signs are the sign here, moment value sign, moment sign is given here as positive. Why it is positive? We'll check whether it is negative. Why why had become positive? We'll check that. So inertia moment, we know that it is acting in clockwise direction because I have displaced the bob in counterclockwise direction. So the inertial moment or the inertial torque is acting in clockwise direction. So if the moment due to spring force is in clockwise direction, we will take it as positive. And moment due to weight is in clockwise direction, then we will take it as positive. Otherwise, we will take it as negative. So what is the directional moment due to spring force? It is acting towards left direction, you know that. And this is the perpendicular distance A cos theta. So with respect to O, this is creating a clockwise moment. Kx is creating a clockwise moment. Okay, you can see this. I am rotating the pointer. Okay, you can see that. So about O, Kx is creating, that is spring force is creating a clockwise moment. That is why here it is given as positive. Okay, now we will check for weight, the moment created by the weight. You can see W like this, it is acting vertically onwards. The L sin theta is the perpendicular distance of weight with respect to point of oscillation. So with respect to point of oscillation, this W is creating a clockwise moment. You can see here I am rotating the pointer. So W is creating a clockwise moment. with respect to point O, because W is acting downwards. That is why it is also taken as positive, because inertial force is inertial torque is actually clockwise, spring torque is actually clockwise, and the torque due to the weight is also actually clockwise. So everything has been taken as positive. Okay. So net moment due to the system of forces plus inertial torque or inertial moment is equal to 0. D-level principle is written. Now I'll write moment of inertia of the slender bar or this long pendulum. It is ml square, mass into length of the pendulum square. That is the equation for moment of inertia, mass moment of inertia of the pendulum. Okay, ml square. You have studied this in mechanics, I think. So we can use that equation ml square in theta double dot plus ka square mgl theta. Okay. Now we can rewrite this equation like this. Okay, I'm dividing the equation with the ml square. Now we'll compare the equation which we have derived. This is actually the equation of motion. So our first aim objective has been we have completed our first task, our first aim. Our first objective is to find out the equation of motion. So this is our equation of motion. Now we will compare this equation of motion with the general form. General form is, we know that for a longitudinal system, or system moving up and down with respect or in the direction of axis of the system, it is called longitudinal motion. In that case, we will write the equation or the linear motion. System having a linear motion. Here it is not linear motion, it is actually having a rotational motion. So, or angular motion. So if for a system having linear motion, equation of motion is mx double dot plus kx equal to 0. Here it is I theta double dot plus k theta equal to 0. I theta actually represents inertial torque. K theta represents the moment due to the forces, spring force, weight, everything. Okay. So the other one is mx double dot plus kx equal to 0. Mx is inertia force due to linear motion plus net force acting on the system. That is kx. If there is only spring, then there is spring force. So mx double dot plus kx equal to 0. That is the equation for longitudinal vibration. For our case, it is transverse vibration. So we'll take rate of change of angular momentum plus equal to net torque acting on the system. Or in other way, we can see inertial torque plus net moment due to other forces will be equal to 0. So inertial torque I theta double dot plus k theta is equal to 0. That is the general form of for transverse vibrations. So we can rewrite this equation like this: theta double dot plus k by I into t equal to 0. This k by I is actually the angular frequency. We have discussed this in the previous presentation on derivation of equation motion for transverse vibration, derivation of equation motion for longitudinal vibration. All those things we have discussed in the previous presentation. In that we have discussed for transverse vibration is root k by I. Root k by I is actually the equation of motion for or the natural frequency for the transverse vibration system, root k by I. Okay, so k by I is the value omega n square. Okay, root k by I is omega n. So omega n square is this. When comparing that with our equation motion, it is this. You can see. So omega n square is this in our case. So omega n will be root of that. So in radians per second, you will be getting the equation. This is the regular frequency in radians per second. If you have to convert that unit, if you have to convert our equation or our answer or our expression to hertz, then you need to multiply omega n with 1 by 2 pi. So 1 by 2 pi into omega n is fn, which is in the natural frequency system in hertz. 1 hertz is equal to 1 cycle per second. Okay, 1 hertz is equal to 1 cycle per second. If you have to convert that from radians per second to hertz or 1 cycle per second, we need to multiply it with 1 by 2 pi. Okay, so 1 by 2 pi into omega n is fn, which is in hertz, natural frequency in hertz. So this is the how we have derived the equation of motion, and now we have extracted the natural frequency from that equation of motion by comparing with general form. So that's our problem. We have found out the natural frequency. Second question: determine the natural frequency of spring mass pulley system as shown in the figure. This also have an angular motion. You can see the pulley will have an angular motion. The pulley is having actually a torsional vibration. And now, but the mass which is attached to the pulley is having a longitudinal vibration. So either you can solve, either you can write equation motion of that pulley, or you can write equation motion of that mass and find out the natural frequency. You can use two methods. Either you can go for Newton's method, or you can go for energy method. This problem I will solve by using both these methods, Newton's method and energy method, so that you will understand how we can do the same problem by using Newton's method and energy method. So this problem is asked for KT examination in December 2018. Okay. Okay. We will first draw the free body diagram for the problem. We can draw the free body diagram for the pulley and also draw free body diagram for the mass. In this problem, you can see the pulley is undergoing a torsional vibration and the mass is having a linear longitudinal vibration. Pulley is having angular displacement, mass is having a linear displacement. We can first of all we will give a initial displacement to the pulley or mass. I am giving a angular displacement for the pulley in the counterclockwise direction. You can see from the figure I am giving a counterclockwise direction angular displacement. You can see here theta is in the counterclockwise direction. You can give the displacement clockwise direction also, no problem. Anyway, first of all we need to give a initial displacement either in counterclockwise direction or clockwise direction. So here I am giving a counterclockwise direction. So when I am rotating the pulley or twisting the pulley in counterclockwise direction, the spring will get stretched. Spring will get stretched. You can see the spring will get stretched. I am using the pointer to show that spring will get stretched, so that the spring will try to push the pulley downwards. That is why spring force has been represented downwards. Okay, when the pulley is rotated counterclockwise direction, spring will get stretched, and so that the spring force will be acting downwards. You will try to bring the pulley to the previous position by pulling downwards. That is why spring force is acting downwards. The second force is inertia force of the mass. When the pulley is rotated counterclockwise direction, the mass will be moving downwards. So the inertia force of the mass will be acting upwards. Okay, inertia force of the mass will be acting upwards. That is why it is shown here upward direction. So both these forces are tangential, the tangential direction to the circle of that pulley. Okay, so two forces are there: spring force, inertia force. So when the pulley is twisted counterclockwise direction, spring force will try to pull it down, and inertia force is dialed to push it up. Okay, so spring and inertia forces. So I hope you understood the direction of the forces. We can see here the mass, free body diagram of mass also. When the mass is moving downwards, we know that when I am rotating the pulley in counterclockwise direction, mass will move downwards. So when the mass is moving downwards, the spring will try to pull. You can see in this side, the spring force will be acting upward direction, because the spring is trying to bring the pulley to the original position. That means it will push the mass like this. Push the mass like this. When we are rotating the pulley in counterclockwise direction, it will push the spring will try to push the system like this. Okay, like this. So that is why spring force is shown here. And mx double dot, that represents the inertial force of the, or the direction of inertial force of the mass. The mass is moving downwards, so the inertial force will be upwards. That is mx double dot. That is inertial acceleration will be upwards when the mass is moving downwards. So inertial force will be acting upwards. That is why it is shown here. Okay. Uh, these are the notations we are using. Capital M represents mass of the pulley. Small m represents the mass of the solid body. That is a small m. Spring deflection. Okay, x. So you can see here, when I am rotating the pulley in counterclockwise direction, spring will be stretched or spring will be deflected. That deflection will be equal to the value r theta. Okay, it is approximately equal to r theta. R is the radius of the pulley. Theta is the angular displacement I have made on the pulley in counterclockwise direction. So r theta will be the actually the displacement of the or the stretching of the spring. Okay, so x, that is stiffness, spring deflection, it is taken as r theta. So we need to find out if you want to find out similarly, if the mass will be also moved downwards by a value r theta. You know that. Okay, when the spring is stretched by value r theta, mass will be moving downwards by value r theta. Okay, when the spring is stretched by value r theta, mass will be also moving downwards by value r theta. So you can say velocity of the mass is x dot, that is d by d theta of r theta, d by dt of r theta, that is r into theta dot. Okay, similarly for finding the acceleration mass, you need to again differentiate velocity dx dot by dt or d square x by dt square. Okay, that is x double dot, which is equal to d square r theta by dt square, that is r theta double dot, r theta double dot. Okay, so x double dot is r into d square theta by dt square, that is x double dot is equal to r into theta double dot. Understood? I hope you understood. So x is r theta, x dot is r theta dot, x double dot is r theta double dot. Okay, r is always constant, radius of the pulley, radius of the pulley. So by applying Hilbert's principle, we have discussed in the previous problem also, Hilbert's principle, that is the inertial torque of the system will be plus the moment due to the system of forces about a point of reference. Here the point of reference is the center of the pulley. Okay, so inertial torque of the system plus moment due to the system of forces about the center of the pulley will be equal to 0. So system of forces means we have two forces, that is spring force and inertia force. So moment due to spring force about the pulley center and moment due to inertia force about the pulley center. So we need to find out two moment. Okay, one due to the spring force, another due to the inertia force, plus the inertial torque will be equal to 0. So what is the direction of inertial torque? We have discussed that in previous problem also. Here what is the direction of inertial torque? I am giving an initial displacement in the counterclockwise direction, so the inertial torque will be in clockwise direction. Understood? I am giving, you can see here in the diagram below, I am giving the displacement in counterclockwise direction, so the inertial torque will be in clockwise direction. So inertial torque direction is clockwise direction. So you remember that. So inertial torque is I theta double dot, we know that, I alpha or I theta double dot. I is the moment of inertia, mass moment of inertia of the pulley. I am now writing the equation motion for the pulley, not the mass. Either you can write the equation motion of pulley or you can write the equation motion of mass. I am now writing the equation motion of the pulley. So inertial torque of the pulley is I theta double dot. I is the moment of inertia of the pulley. I will be mr square by 2. Why it is mr square by 2? For a solid disk, you might have studied in mechanics. For a solid disk, radius of gyration of the solid disk is r by root 2. Radius of gyration is r by root 2. Moment of inertia is mass into radius of gyration square. So mass into m into radius of gyration is r by root 2 whole square. So m into r square by 2. Okay, m is the mass, radius of gyration is r by root 2. So k square is r by root 2 whole square, that is r square by 2. So mk square is mr square by 2. So mr square by 2 into theta double dot, that is the inertial torque of the pulley. It is acting in clockwise direction, that you have discussed. It is acting in uh, clockwise direction, because I am giving the it is acting counterclockwise direction, because I am giving the displacement in counterclockwise direction. So inertial torque is acting in clockwise direction. Okay. Next is spring force. Spring force, you know, kx. X is deflection. Deflection is r theta. So k into r theta. Moment due to the spring force about the center of the pulley. It is force into distance. What is the distance of this force with respect to center of the pulley? R. So k into r theta into r, k r square theta. Similarly, moment due to the inertia force, mx double dot into r, mx double dot into r. Okay, mx double dot is inertia force, r is the distance between the inertia force and the center of the pulley. R x double dot is, you have found it here. Okay, x double dot is r theta double dot. So m r theta double dot into r, m r square theta double dot. So you can write the D'Alembert principle. You have write the equation motion, that is mr square by 2 into theta double dot plus kr square theta plus mr square theta double dot equals 0. So inertial torque, moment due to spring force, moment due to inertial force equal to 0. Why all this have written positive? The sign is, why it is positive? Sign is positive because we know that inertial torque is clockwise direction, because we are giving a displacement in counterclockwise direction. So the initial torque is clockwise direction. Spring force, it is acting downwards. It is creating a clockwise effect. It is creating a clockwise moment, okay, on the pulley. That is why it is positive. Inertial moment is positive clockwise. Spring moment due to spring force is clockwise, so it is positive. I will check for inertia force. Inertia force is acting upwards. With respect to the center of the pulley, it is creating a clockwise moment. So both these two forces are creating a clockwise moment. Inertial torque is clockwise. That is why everything has taken positive. So inertial torque is clockwise. Moment due to spring force is clockwise. Moment due to the inertia force is clockwise. So everything positive equal to 0. I have rewritten the equation like this. Now comparing with the, okay, you can rewrite the equation like this. Okay, taking the common terms. Understood? So comparing this with our general equation. What is the general equation? I theta double dot plus omega n square theta equal to 0. So this term which I have highlighted here is omega n square. Okay, so omega will be root of this. Okay, this is same as what you discussed in the previous problem also. So theta double dot plus omega n square into theta equal to 0. That is our general equation. So omega n square is the term which is lying near to theta. So omega n square is the term which is lying near to theta. So omega n will be root of that term. Okay. So this is in radians per second. So if you want to convert omega n square to hertz, that is if you want to convert radians per second to hertz, then we need to multiply omega n with 1 by 2 pi. So 1 by 2 pi into omega n, which is represented as Fn, natural frequency, in hertz. Okay, so this is how we are finding out natural frequency of a system by using Newton's method. Understood? Let's do the same problem by using energy method. Okay, that will be discussed in the next slide. Okay, so we'll discuss the same problem in energy method also, because we can use any of this method for solving problem. Okay, so energy method, we know that total energy system remains constant. So what are the elements in this system? There is a pulley, there is a mass, and a spring. So total energy of system will be the kinetic energy of the mass M, kinetic energy of the pulley capital M, okay, and also strain energy of the spring or the potential energy of the spring. So there are three energies. One is the kinetic energy of small mass M, and the kinetic energy of the pulley M. Another one, the strain energy of the spring, or the strain energy of the, or the potential energy of the spring. Okay, so according to energy method, the concept is a total energy system remains constant. Okay, so I'm writing the equation like this. First term actually represents kinetic energy of mass, small letter m, half m v square. V is velocity, that is x dot square. Next is kinetic energy of pulley, half, instead of m, if this is a rotating body, so instead of m we need to use moment of inertia. So that is the main difference between rotating parts and translating parts. The first one is a translating body, that is it is a linear motion. Second one is a rotating body. So kinetic energy is half I into omega square. Okay, omega is what is theta dot. Theta dot is omega, that's angular velocity, omega. Rotating part, the angular velocity of rotating part. Okay, so half I into omega square, or half I into theta dot square, that is the kinetic energy of pulley. Similarly, the last term, that is strain energy of the spring, or potential energy of the spring, half kx square. K is the stiffness of the spring. Okay, so total energy is a constant, that is what is written here. So why x dot is written as r theta dot? That I have explained in the previous slide. That is, x is r theta, x dot is r theta dot, x double dot is r theta double dot. Okay, so x dot square is r theta dot all square, that is r square theta dot square. Okay, here x is r theta, r square theta square. Okay, now mass moment of pulley, this is we have discussed in the previous slide. Mass moment of pulley, we know that mr square by 2. Why it is mr square by 2? Once again I will explain. Mass into radius of gyration square, that is moment of inertia of the pulley. Radius of gyration of the pulley or radius of gyration of disk is r by root 2. So m into r by root 2 all square, that is mr square by 2. Now substituting all these things in that equation and then differentiating that equation with respect to time. Okay, differentiating the above equation with respect to time. This equation is differentiated with respect to time. So d by dt of 1 by 2 into mr square theta dot square, it will be like this: 1 by 2 into mr square into theta dot square. What will be the final form? 1 by 2 into mr square into theta dot square. Theta dot is written as 2 into theta dot into theta double dot. So 2 cancel. Okay, 1 by 2 and that 2 cancelled. That is why there is no 1 by 2 here. Okay. Similarly for this case, half into I into theta dot square. Differentiating this, what do we get? This. That is half into I into 2 theta dot into theta double dot. Half into I into 2 theta dot into theta double dot. 2 cancel. There is no 2 here. Okay. Similarly here, half into k into r square into 2 theta into theta dot. 2 theta into theta dot. So that 2 and 2 cancel. Okay. So understood how it is differentiated? Equal to, or differentiating constant we will get 0. Differentiating constant we will get 0. Okay. So rearrange this equation, you will get like this. So this is the same equation which we have got when by using Newton's method. Okay. So this part of the equation is the natural frequency, omega n square of the natural frequency. So root of that will be the natural frequency value, or root of that will be the expression for natural frequency. If you want to convert that to hertz, then multiply with 1 by 2 pi. Okay. I hope you understood the equation. You understood the problem. So by using both Newton's method or by using energy method, you can solve the same problem. So that's your choice. So these are the references for this presentation. Theory of machines by S.S. Jithin, mechanical vibrations by VP Singh, mechanical vibrations and inertial noise control for Jithin LG. There are a lot of problems discussed in VP Singh, mechanical vibrations by VP Singh, and also mechanical vibration and inertial noise control by Jithin LG. You can go through those problems related to this session. Okay.